A supermassive black hole consumes the equivalent of one Earth every second. It's stunning and compelling to witness the first-ever image of a black hole in space. Black holes are cosmic giants that devour everything in their path, including light itself. These black holes were formed from the dying remnants of enormous stars and have gravitational pull so strong that they distort space and time, entangling everything inside their gravitational grasp, including time itself. Now, a discovery uncovered by the James Webb Space Telescope challenges the fundamental basis of our knowledge. Just how does this discovery cast doubt on our long-held beliefs about how galaxies came to be? Does this cosmic aberration pose a threat to Earth? Join us as we explore how the James Webb Telescope has detected a huge dormant black hole near the solar system. Black holes are a tricky bunch. It was quite a challenge to search for the first one, even though Einstein's theory of relativity predicted their existence. Black holes, in contrast to stars, do not give off any light of their own, making their size and spectra the only measurable properties. We now have photographic evidence of black holes, confirming their existence. However, conclusive proof of black holes was lacking for quite some time. For scientists, SGRA* was the first to be found in 1964. Stephen Hawking and Kip Thorne, two of the foremost authorities on black holes, did not reach a consensus on whether SGRA* was indeed a black hole until over 30 years later. Hawking was quite certain that black holes existed. They were, after all, a major emphasis of his professional life. However, the question of whether scientists could actually locate one remained unanswered. Naturally, Hawking was a little anxious about the lack of findings, so he hedged his bets with his studies. He also mentioned that he and Thorne were almost positive that SGRA* was a black hole in 1975 when the wager was initially cast. They were both 95% sure. By 1988, according to Hawking, they still came to an agreement but couldn't finalize it until they were absolutely certain. Hawking was compelled to relinquish the bet in 1990 when more observations of the system had accumulated sufficient proof that it contained a black hole. Thorne claims that Hawking waited for the right time to concede defeat. 2 gear counters were launched into space on a suborbital rocket, leading to the initial discovery of SGRA*. A signal was detected by the gear counters, which astronomers were able to pinpoint to a system 7,200 light-years away, featuring a blue supergiant star surrounding another large object. The second object was also strongly radiating X-rays, which would make sense if it were a black hole. Much research has focused on SGRA* since it was discovered in 1964 as the first black hole in the universe. However, it still has more surprises in store for scientists. New research shows that the black hole is 21 times the mass of the Sun. This object has the distinction of being the largest stellar mass black hole ever found without the utilization of gravitational waves. This new finding casts doubt on astronomers' long-held assumptions about black hole formation. The stellar winds that blow from a star's surface cause the star to lose mass to its environment. However, if we want a black hole this massive, we must reduce the mass loss experienced by brilliant stars over their lifetimes. SGRA* breaks records in more ways than one. Its extraordinary bulk is only one of them. SGRA* has the fastest rotational velocity of any black hole discovered so far, approaching the speed of light. A black hole with such a high spin also doesn't follow the accepted pattern of black hole evolution. Although definitive evidence of black holes has only just been discovered, it is becoming more apparent that they are scattered throughout the universe. Therefore, even if astronomers eventually untangle all the mysteries of SGRA*, the first of its kind, its countless kin still hold many surprises. Less than 2,000 light-years away from Earth, scientists have discovered a sleeping giant, the Milky Way's largest stellar black hole with a mass 33 times greater than that of our Sun. Despite being the second closest known black hole to Earth, the dormant Gaia BH3 had remained undiscovered until it was discovered by accident in a deluge of data and observations gathered by scientists from the European Space Agency. Gaia BH3 is located in the constellation Ala, the Eagle. The group noticed something out of the ordinary as they went through data from the agency's Gaia mission, which is creating a three-dimensional map of our galaxy. A star that was wobbling 1,926 light-years distant had a peculiar trajectory that pointed to its being ensnared in an orbit by a neighboring massive black hole. To confirm the mass of Gaia BH3, the astronomers and ground operators utilized a very large telescope of the European Southern Observatory in Chile to validate their discovery. They revealed that once every 11.6 years, the wobbling star completes one orbit around the black hole. The discovery of the nearby undetected high-mass black hole came as a complete surprise to everyone. Gaia BH3 is a type of black hole caused by the collapse of a star known as a stellar black hole, and it's the largest of this type discovered in our galaxy. As a dormant black hole, it isn't actively siphoning energy and materials from a companion star, making it inconspicuous in surveys of the sky. Stellar black holes in our Milky Way typically have a mass around 10 times that of the Sun, with SGRA* holding the record at 21 times the Sun's mass. The Gaia BH3, which has a mass of 33 solar masses, is still tiny in comparison to all black holes. For example, the central supermassive black hole in our galaxy, Sagittarius A*, is 4 million times larger than the Sun. Gaia BH3 is the second closest black hole to Earth, behind only Gaia BH1, which is 1,500 light-years away and 10 times the mass of the Sun. Astronomers now have more evidence to piece together how stellar black holes formed from the demise of long-gone stars, which makes the discovery all the more important. Stars with lower concentrations of heavy metals are thought by astronomers to be the source of more massive stellar black holes. Theoretically, these metal-poor stars, which are mainly made of hydrogen and helium, are believed to experience slower mass loss, leaving more material available to create more massive black holes when they die. But scientists didn't have an example to draw from until they discovered Gaia BH3 and its companion star, which was metal-poor, indicating that the star that generated the black hole was likewise low in metal. On the other hand, using the James Webb Space Telescope, astronomers have discovered an extremely red supermassive black hole growing in the early universe's shadow. As the universe expanded, the supermassive black hole took on a reddish color. This was some 700 million years after the Big Bang. As the universe expands in every direction, the light going in our direction is redshifted, and in this instance, the redshifted light suggests a thick veil of gas and dust surrounding the black hole. Lucas Food and Al Zitron of the Buren University of the NG's astronomy team were able to establish the supermassive black hole's map by analyzing JWST data. Its startling massiveness, at about 40 million times the Sun's mass, stands in stark contrast to the galaxy it inhabits. The group also discovered that the supermassive black hole is quickly devouring the dust and gas surrounding it. It is situated about 12.9 billion light-years from Earth, but its expansion is ongoing. Scientists immediately suspected it was a quasar-like object due to its reddish appearance. Quasars are created when copious amounts of matter surround supermassive black holes. This matter forms a disk of gas and dust called an accretion disk that gradually feeds the black hole. The immense gravitational influence of the black hole churns this matter, generating intense temperatures and causing it to glow. Furthermore, the cosmic titan's poles release any material that does not fall into the supermassive black hole using highly collimated jet particles in these areas that are propelled to speeds close to the speed of light. Bright electromagnetic emissions accompany the eruptions as these relativistic jets are shot forth. Supermassive black holes and active galactic nuclei, AGN, generate quasars, which are so intense that their brightness exceeds that of all the stars in their surrounding galaxy combined. In JWST data, this supermassive black hole appeared as a tiny point due to the enormous amount of radiation it was emitting. The object was determined to be an unusual star-forming galaxy based on color analysis. This provided more evidence in favor of the theory of supermassive black holes. Its small size and apparent supermassive black hole nature stood out from other quasars discovered in those early days. Even with JWST's powerful infrared capabilities, the early quasar wouldn't have been visible if it weren't for an effect that Einstein predicted in 1915. Einstein's theory of general relativity suggests that objects of mass warp the very fabric of space and time, which are truly united as a single entity called spacetime. The theory goes on to state that this curvature is what causes gravity to exist. The curvature of spacetime is more extreme for objects with a larger mass. Because of this curvature, not only do planets learn the proper routes to travel around stars and galactic centers, but the light emitted by stars also changes. The closer an object is to a mass, the more its path is bent. A foreground object or lensing object can alter the appearance of the position of a background object by bending the light path from that object. In extreme cases, the effect might make the background object seem in more than one location in the same sky image. On other occasions, the object in the backdrop is merely exaggerated due to the light being amplified. We call this effect gravitational lensing. With the help of a galaxy cluster known as 2744, the JWST was able to magnify the light of faraway galaxies in the background that would have been invisible without it. This unveiled the crimson quasar that had been their target, which had initially appeared as 3 red spots. This new information adds to the growing body of evidence that the early cosmos was populated with supermassive black holes, which can be millions or even billions of times heavier than the Sun. Now that this behavior has been observed in multiple additional early universe supermassive black holes, it sheds light on the growth of both the black hole and the host galaxy, as well as the interaction between the two, which is still mostly unknown. It's similar to the classic chicken or egg dilemma, but with an astronomical twist. At this time, we have no idea which came first, the galaxy or the black hole. How massive the first black holes were and how they grew is still unclear. Researchers may have discovered proof that microquasars, which are vampire black holes that devour stars, are the cosmic particle accelerators that unleash the unexplained high-energy cosmic rays that hit Earth. These massive black holes eat the material from nearby supergiant stars in binary systems. After being directed toward the black hole's poles, some of the star matter is ejected as relativistic jets traveling at great speeds. A microquasar is a relatively mild version of a quasar, both of which are fueled by enormous supermassive black holes that devour matter in their immediate vicinity. First discovered in 1912, cosmic rays can hit our planet with staggering energies, reaching 10 to the power of 20 electron volts eV, which is way more energetic than the particles accelerated at the Large Hadron Collider, Earth's largest and most powerful particle accelerator. Accordingly, the hypothesis has it that the universe's most potent cosmic particle accelerators are supernovae and microquasars. As a result, these occurrences are being considered as potential causes of the high-energy cosmic rays. But evidence of microquasars accelerating particles to such high energies has been scarce until now. Using the high-energy stereoscopic system, HESS, to identify exceptionally high-energy gamma rays emanating from the jets of the most powerful microquasar in the Milky Way, the team established the link between cosmic rays and microquasars. This is known as SS-433. The SS-433 jets collide with the surrounding matter, producing a shock front that accelerates electrons to speeds large enough to explain the particles seen in high-energy cosmic rays, resulting in the creation of these gamma rays. Although the acceleration mechanism in SS-433 jets is comparable to that in a supernova remnant, the shocks in the former can propel particles to greater energy due to their greater speed. The extremely powerful photons picked up by the SS-433 large-scale suggest, in a roundabout way, that we shouldn't ignore these objects when trying to explain the most powerful nuclei in cosmic rays from a galactic center. SS-433 was actually the first microquasar ever discovered. Its existence was first revealed in 1975, and it was named SS-433 after being included in a 1977 catalog of celestial bodies. It later rose to fame when science fiction author Arthur C. Clarke named it as one of his alternative 7 wonders of the world. A white supergiant star and a black hole with a mass about 10 to 15 times that of the Sun make up SS-433, which is located at the center of the supernova remnants known as W50, about 18,000 light-years away from Earth and affectionately called the Manatee Nebula. SS-433 has been the subject of extensive research for decades. The two are separated by about 15 million miles and orbit each other approximately once every 13 Earth days, with a separation of only about 1/3 the distance between Mercury and the Sun. The star companion of the black hole in SS-433 can be stripped of its outer layers by the tremendous gravity of the black hole. A portion of this stripped material is fed into the black hole, and the rest forms an accretion disk surrounding it. By use of extremely strong magnetic fields, other components of the material are drawn to the black hole's poles. The resulting cloud of material is then ejected at a velocity approximately 26% lower than the speed of light. These jets twirl in a corkscrew-like pattern and are so powerful that they even shape W50. The W50 supernova remnants were formed when a huge star burst around 20,000 years ago. The two bulges or humps caused by the microquasar inside W50 give it the look of a huge cosmic manatee, which is the reason for its vibrant name. Radio waves that are approximately 1 light-year distant from the source can be used to detect the jets of SS-433. At some times, they fade until they are no longer visible due to energy loss. Curiously, these relativistic jets resurface in high-energy X-ray photons some 75 light-years away from where the microquasar originated. The group concludes that this proves that the particles shot out from a black hole are being propelled to even higher energy and speeds by something inside each jet. The 5 Namibian telescopes that make up HESS were used to study these peculiar gamma-ray jets coming from SS-433, and the results showed that the binary system was further away from the source of the higher-power gamma rays. The group concluded that gamma rays, which are particles of infrared light, are best explained by high-speed shock-accelerated electrons in 2 locations around 75 light-years from the center binary of SS-433, where shocks are bending jets into a tight column and enhancing the energy of the accompanying particles. The team will now try to uncover the remaining mysteries surrounding this fascinating microquasar. As part of this process, we must identify the source of the jet shocks, which have been detected at a distance from the binary system from where they originated. Additionally, the group will try to generalize their knowledge of microquasar jets to jets emitted by larger quasars driven by supermassive black holes. Furthermore, although these results clearly point to a potential origin for high-energy cosmic rays, they do not yet resolve the cosmic mystery that has persisted for a century. Black holes, dark energy, and many more will be among the goals of the James Webb Space Telescope in the coming years. Exploring primordial quasars and the characteristics of the first black holes are 2 of the many topics covered by the JWST Cycle 3 supermassive black hole observation missions. Over the course of billions of years, scientists are hoping to deduce how these black holes may have affected galaxy formation. How these cosmic behemoths attained their enormous masses prior to the universe being 1 billion years old may be unearthed by JWST investigations of supermassive black holes in the early universe. With the help of JWST, we can find out whether a massive molecular cloud that formed around 13.2 billion years ago may have collapsed directly, giving rise to a heavy black hole seed and explaining how the universe expanded so quickly. Examining objects from the early cosmos is one of the main responsibilities of JWST. While the primary goal of JWST design was to study objects far away, the observatory will also be utilized to investigate objects within our solar system during Cycle 3.